Alright, logic fans, welcome to 3.5b, our second video on section 3.5, and we left off talking about a syntactic deduction and sort of explaining the ins and outs of this definition by looking at an example of an actual syntactic deduction, the same thing you've always seen. Now, moving on to the notion of a syntactic proof, okay? A syntactic proof is really just like a syntactic deduction with one minor alteration. So we're going to leave this same definition up here. A syntactic proof is also an n by 2 grid, okay, just like this guy, where every quadrant in the leftmost column contains exactly one string and every quadrant in the rightmost column indicates whether a string to its left is a premise axiom or follows from one or more strings by a syntactic rule, except a syntactic proof has no premises, so we're going to delete this. So whether the string to its left is an axiom or follows from one or more rules, one or more strings by a syntactic rule. So, for example, this right here, this is a syntactic deduction, but it is not a syntactic proof. It is not a syntactic proof because syntactic proof, by definition, does not have premises. And as you can see, this one does have premises, okay? But the one we did a minute ago, which looked like this one here, this was a syntactic proof, right? Because it's a syntactic deduction without any premises. And we used an axiom to get started. In this case, we used LEM, our first axiom, to get started. So this is a syntactic proof, all right? So as you might have caught then, every syntactic proof is a syntactic deduction, but not vice versa. So, for example, let's pull up the other one again. So this here, this is a syntactic proof, okay? It's also a syntactic deduction, okay? But this one here, this is a syntactic deduction and not a syntactic proof. And it's not a syntactic proof precisely because it has premises, and syntactic proofs cannot have premises. That's the concept, that's the definition, it's that easy. Every syntactic proof is a syntactic deduction. Not every syntactic deduction is a syntactic proof. For example, this one. Okay? All right. So, pretty straightforward. Now, let's go on to the definition of a theorem, which is very easy. Okay? So, a theorem, okay, is any string of symbols, right, like this or this or this, which is the last line of at least one syntactic proof. Now, this was not a syntactic proof, but the other one was. Let's get that one. Okay, so this here was our syntactic proof, okay? And a theorem, by definition, is any string which is the last line of at least one syntactic proof. Well, here's a syntactic proof. Here's the last line. And so this string, A implies A, okay, A arrow A, is in fact a theorem by definition. And we say that it's a theorem by using this turnstile symbol that we discussed. And this says it is a theorem of logic that A implies A. And here is your syntactic proof that A implies A is in fact a theorem of logic, okay? And that's what we mean by a theorem. Last concept, which is really easy, is the notion of syntactic validity, okay? And again, you've already been using this concept. We're just formally regimenting it now. Let me put it up here along with an example. So an argument, for example, this one right here, here's an argument. Notice it has premises, okay? An argument is syntactically valid, right? So we talked about semantic validity, and that had to do with what happens on the argument's truth table. Well, an argument is syntactically valid if and only if its conclusion, in this case it's B, can be syntactically deduced from its premises. And notice syntactically deduced is this concept, if and only if there is a syntactic deduction of its conclusion from its premises. And so this argument here that we just pulled out of a hat at random is in fact syntactically valid, and you can demonstrate that it is syntactically valid by providing a syntactic deduction of its conclusion from its premises, like this one. This is a syntactic deduction showing that its conclusion can be syntactically deduced from its premises, and so this argument is by definition therefore syntactically valid, okay? And so I hope you're tracking all of these concepts, and you should take some time to maybe practice talking about them with a friend or with your instructor. But you know, a theorem basically is the last line of a syntactic proof, and an argument is syntactically valid provided you can provide a syntactic deduction of its conclusion from its premises. That's the big idea, and a syntactic proof just is a syntactic deduction without any premises. Okay, that's the whole concept here. These are really important ideas, and I hope you're tracking them. I want to emphasize one more time that if you plug this argument into a truth table sort of analysis, you will find that it's semantically valid. So on a truth table, it turns out to be valid. But also, it is syntactically valid, meaning you can move from the premises to the conclusion using our syntactic rules. Now, it's a higher level concept that every argument which is semantically valid is syntactically valid, and vice versa. If you're syntactically valid, then you're semantically valid. So that's a nice thing to keep in mind. We're not going to go into that. That's beyond our scope. Those are soundness and completeness proofs. You should discuss them with your instructor, but they are beyond our scope. But I thought I would point them out. I also thought I would point out that, so there's two important points here about theorems. So here's our one and only theorem thus far, but noticed, and as we noted, it is a logical truth. It is a tautology. All theorems are tautologies, and every tautology, so everything that turns out to always take the value true on a truth table, can be proven in our system. So it's 2 points. If you're provable syntactically, if you're syntactically provable, then you're a tautology. So if you're not a tautology, you're not syntactically provable. And every tautology is syntactically provable. Again, we're not going to demonstrate those things, but they're useful concepts to have in mind. In other words, there's no point in trying to syntactically prove, right? There's no sense in trying to prove a sentence, a string like this, because this is not a tautology, okay? And only tautologies can be proven, and all tautologies can be proven. Okay, so useful stuff operating in the background, but let's do some more work with our axioms. Okay, so the primary function of our axioms, and the one we've discussed so far is LEM. We have another one we'll discuss, but the primary function of our axioms is to be able to prove theorems. Okay, we just talked about what that means. Basically, to syntactically deduce strings like this from no premises. Okay, so we did this one, but you know, when you start off doing this, your instructor puts this in front of you and says, prove it's a theorem of logic that A implies A. And you're sort of like, okay, I've got no premises. How am I supposed to get started? I'm supposed to have a syntactic proof, right? None of these are going to be premises. And somewhere at the end of it, I'm supposed to get this thing out of it, right? And I've got to use one of my axioms, and you know, in this case, you know, we know it's going to be LEM because that's the only one we've discussed. But I've got to use one of my axioms to get started, and then I've got to manipulate it. I've got to manipulate that axiom string until I get this string, okay? The string that I'm asked to get. In this case, A implies A. And the question is how the heck do I know how to get started here, right? Well, experience, looking at lots of examples, creativity, all those kinds of things play a very important role. Practice is absolutely critical. However, in the text, I've developed this idea that I call reverse engineering, and it's sort of a technique to help you figure out how to prove theorems, okay? So what I want to do here is walk you through how the reverse engineering technique works, and you can use it on any theorem you're trying to prove. Let's use this one. What I want to do is I want to sort of, you know, we're going to have our official proof over here. This is our syntactic proof. Okay? Over here, this is just some scratch work we're going to do on the side before we write up our formal proof. The scratch work is going to say, okay, let's suppose we had this sentence available. We don't actually have this sentence available. It's what we're trying to prove. It's going to be the last line, so we don't have it available yet. But let's just pretend for a second we have it available, and who knows how the heck we got it or where it came from. Okay? Well, what I want you to do now is I want you to start manipulating this thing, and you know that you're going to have to use, LEM at some point. One of these first lines is going to be an axiom. It's going to be one of our two axioms. Let's suppose, it's going to be P or not P in this case. All right. You want to start applying rules and manipulating this thing until you find a P or not P. So, can you see what kind of rule you could possibly apply to this sentence? Any of our syntactic rules. Pause now. Okay, you're going to look at a syntactic rule, right? It's going to typically be a rule of replacement rather than a rule of inference, because you're going to be manipulating one line. Okay, so you're looking to manipulate this, and so you're looking for a rule of replacement that applies to conditionals. Well, we have a couple of them, but if you look at them, you might hit on this particular sentence, right, which we get from impla. So that was impla on 1. And again, this is just some scratch work we're doing on the side. We're not writing our formal proof yet. We got impla, and I'm looking for something of the form of one of our axioms, P or not P. Okay, and if you look at this, you already see it pretty closely. But even if you can't quite make it out yet, you can of course get it the rest of the way by doing this, right? And now P or not P is absolutely explicit. Okay, and now that you've got your P or not P, now that you've found one of your axioms, in this case LEM, you're sort of done with the reverse engineering project. And so you can say, okay, I'm going to start with A or not A, and I'm going to say that that's the law of excluded middle. Okay, so now I'm going to write up my formal proof. And then I know I need to switch from this to this. And it's like, oh, how do I do that? Oh, well, it's just sort of reading this backwards, right? You're just sort of going from this line up. Okay, so I'm going to go not A or A. And of course, that is com on line 1. Okay, and then, of course, I need to get from this line, not A or A, which is what I have here, to this line, which is if A, then A. And so, bang. And how did I get from line 2 to line 3? Well, I used impla on line 2. And that, of course, is QED. So let me delete these guys out of here. Turns out I didn't need them, all that space. And bang, here is my syntactic proof of this string being a theorem of bivalent logic. Okay? And I figured out how to get started and how to do it by reverse engineering this thing, basically starting with the sentence in question and manipulating it using rules until I could see one of my axioms. Okay? All right, we're going to keep working on this. We're going to keep talking about axioms and looking at lots of examples, but I want to not rush us, so let's go to the next video. See you on video 3.5C.